Hello, this is Miss Moore, and today during chemistry we're going to discuss net ionic equations. Today's essential question: how are net ionic equations written? For today's lecture, you will need available your periodic table, polyatomic ion chart, and solubility rules. Net ionic equations are related to double replacement reactions, so let's do a real quick review of double replacement reactions. So, for a double replacement reaction, if solutions of two ionic compounds are mixed, either an aqueous homogeneous mixture will form an aqueous aqueous, or a chemical reaction will occur, in which case you will form a solid, liquid, or a gas. An aqueous solution of ionic compounds. Quick definition: ionic compounds dissolved in water. So they aren't actually compounds anymore, but separated ions floating in water. A quick example of a double replacement reaction is an aqueous solution of silver nitrate plus an aqueous solution of sodium chloride produces an aqueous solution of sodium nitrate and silver chloride solid. Complete ionic equations, which is the first step to completing a net ionic equation. All right, so a complete ionic equation. A complete ionic equation shows all aqueous solutions as ions instead of aqueous compounds. Okay. All right, so let's learn how to write complete ionic equations. And the example we'll be using is calcium chloride aqueous solution plus an aqueous solution of sodium sulfate produces, well, we'll figure that out. All right, so the first thing you want to do is complete the double replacement reaction. Okay, and as a quick reminder, with a double replacement reaction, the positive ions from the reactants switch places when forming the products. You check the charges and neutralize. And then last step is to check the solubility rules to see if each product is aqueous or if you formed a product, solid, liquid, or gas. All right, well, let's complete this double replacement reaction. So we have calcium chloride aqueous plus sodium sulfate aqueous. Okay. First step is to write the charges. So we have calcium, which is a 2+, and chloride, which is a 1-. We have sodium, which is a 1+, and sulfate, which is a 2-. Okay, and the calcium and the sodium are going to swap places. So we'll end up with sodium hooking up with chlorine. Remember, we don't take the subscripts with us. Sodium is 1+, chlorine is 1-. And the other product is going to be calcium hooking up with sulfate. Okay, calcium being 1+, 2+, and sulfate being 2-. Okay. We'll check the charges, and it looks like everybody's neutral, so let's get rid of all that stuff. And now we need to figure out if our products are aqueous, solid, liquid, or gas. All right, to do that, we need to look at the solubility rules. So we'll start with NaCl, and Na is not on the list on the left-hand side, but Cl is, right? Cl is a halogen. So halogens are soluble, except with bonded with silver, lead, or mercury, which is not the case here, which means that NaCl is going to be aqueous. Okay. And now let's look at calcium sulfate. We've got sulfates right here. Most are soluble except when bonded with calcium, strontium, barium, lead, or mercury. So most are soluble except when bonded with that, so that means this is going to be a solid. So NaCl is an aqueous, CaSO4 is a solid. Okay, so we end up with NaCl being aqueous and SO4 being a solid. So we've completed the double replacement part of complete ionic equations. Okay, we've finished the double replacement portion of the equation, so now we need to finish this up. So the next step is to separate the aqueous compounds into ions. Remember, an aqueous compound really means you don't have a compound anymore, you just have ions floating around in the water. Okay, so we're going to have to separate out CaCl2 because it's aqueous, Na2SO4 because it's aqueous, NaCl because it's aqueous, and not CaSO4 because it's a solid. All right, so how do you separate them out? Everything that's aqueous, separate the atoms, the ions, back into ions with plus sign in between, and write the ion charges because they're no longer neutral, right? They're now separated, so the charges come back. Remember, they're hooked up to make them neutral. Also, really important is to remove any subscripts, because the reason we put subscripts when we're talking about ionic compounds is because we want to show how many of each type of ion needs to be there for them to be neutral. But if they're separated, they're no longer neutral, which means no subscripts. There's no such thing as a diatomic ion. Okay, atoms are diatomic. Hydrogen, nitrogen, oxygen, blah, blah, all of those. If they're atoms, they can be diatomic. No such thing is diatomic ions. Okay, so if there's a charge, no diatomics. All right, so let's go through and separate everybody. So the aqueous solution of CaCl2 becomes the ion Ca2 plus Cl1 minus. Again, no charge there. There is a charge there, no subscript. We also have the aqueous solution Na1 plus SO4 2 minus. Okay, that takes care of the aqueous reactants. If we go to the product side, NaCl is aqueous, so we have Na1 plus Cl1 minus. And then we have the solid CaSO4. Don't want to separate him because he's a solid. Okay, and that's how you write a complete ionic equation. If we were actually interested in writing complete ionic equations, if that was the end product, we would need to go through and balance this, make sure everything's balanced. But the truth is, we're really trying to write net ionic equations. And so writing complete ionic equations is just a step along the way. Okay, let's move on to the point of the entire lecture, net ionic equations. So how is a net ionic equation different than a complete ionic equation? Well, a net ionic equation shows only the product. Remember, solid, liquid, and gas, right? If it's not solid, liquid, and gas, you didn't actually make it. And the reactant ions involved in making the product during a double displacement reaction. Okay? And then we've got this term, which is going to be important in a moment, a spectator ion. A spectator ion is an ion that is on both the reactant and product side of a complete ionic equation. So basically, it's the ions that are not involved in forming the product. Okay? That's going to be important in a few moments. All right, let's go over the steps to write net ionic equations. We're going to use the same practice problem we've been using for the double replacement and for the complete ionic equations. So normally step 1 would be to complete the double replacement reaction, which we've already done. So we started out with an aqueous solution of calcium chloride, added to that an aqueous solution of sodium sulfate, and the products were an aqueous solution of sodium chloride and solid calcium sulfate. Step 2, complete the complete ionic equation. And when we did the complete ionic equation, we ended up with calcium ion plus chlorine ion plus sodium ion plus sulfate ion produces sodium ion plus chlorine ion plus solid calcium sulfate. Okay? All right, next step is to cross out all spectator ions. Remember, spectator ions are ions that appear on both sides of the equation. So let's do that. So we have our complete ionic equation, and let's see, calcium is not an ion on both sides of the equation, so he stays. Chlorine is found as an ion on both sides of the equation, so let's cross him out. Sodium is found as an ion on both sides of the equation, so cross him out. Sulfate is not found as an ion on both sides of the equation, so he stays. Okay, now we're going to rewrite the equation with the stuff that has not been crossed out. So we have Ca2 plus SO4 2 minus produces CaSO4 solid. And the last step is to balance the equation, and it's already balanced. That's how you write net ionic equations. All right, last thing we need to do is try a couple practice problems. If you think you got this and can do it on your own, hit pause and try to do it on your own, and then hit play. If you're not comfortable yet, watch me go through this problem. Then you can try the second one on your own. All right, so the first thing we're going to do is rewrite this. So we have lead nitrate, which is aqueous, plus hydrogen sulfate for now, which is aqueous. And we need to write our charges. Lead is one of those guys where we can't figure out its charge by looking at the periodic table, so we're going to have to look at the anion and go backwards. So we have nitrate, which is 1 minus. There are 2 of them, which means lead has to be 2 plus. Okay, and then we've got hydrogen sulfate. Hydrogen, being that it's written first, this is going to be an ionic compound. H has a 1 plus charge, sulfate a 2 minus charge. Okay, and from here, the positives are going to switch places. So we have Pb, let's see, no, we have H 1 plus hooking up with NO3 1 minus, and we have Pb 2 plus hooking up with SO4 2 minus. And when we check out the charges, it looks like everybody is neutral. So now what we need to do is figure out if these are aqueous or solids. All right, so we have our products, HNO3. NO3 is a nitrate, and all nitrates are soluble. So that means HNO3 is going to be an AQ. And we have our product, possibly, PbSO4. Sulfates, most are soluble unless bonded with, that lead's there, so this is going to be our solid. Okay, so we now have aqueous HNO3 and solid PbSO4. Okay, so that's our double replacement reaction. We don't need to worry about balancing because we're not actually done with the problem yet. Okay, next step is our complete ionic equation, which means take all the ions, separate them, take all the aqueous, right, and separate them out into ions. So we have Pb 2 plus NO3 1 minus plus H 1 plus SO4 2 minus produces H 1 plus NO3 1 minus plus are solid PbSO4 solid. Okay, so now to complete the net ionic equation, we need to cross out all ions that occur on both sides of the equation. Lead is an ion on the reactant side, but is combined to make a solid compound, so he's staying. Nitrate is an ion on both sides of the equation, so he's going. Hydrogen is also an ion on both sides of the equation, both reactant and product, so he's going. Okay, so the guys I crossed out, what do we call those? Those are the spectator, right? Spectator ions. So spectator ions, would be nice if I knew how to spell. Spectator ions get crossed out. Okay, and sulfate is an ion on the reactant side, not on the product side. Okay, so now we can finally get to our net ionic equation, which is to write the ions that are involved in making the product and the product. So we have Pb 2 plus SO4 2 minus produces PbSO4 solid. Okay, and what you'll notice, and this is important, when we go to balance, you need to look at two things. Do we have the same number of charges on both sides of the equation? Same number of positives and negatives. If we don't, we need to put a coefficient to fix that. Also, do we have the same number of leads on both sides of the equation? Yes. Do we have the same number of sulfates on both sides of the equation? The answer is yes. All right, so this would be the final answer for the net ionic equation for number 1. Okay, this time if you didn't hit pause before, hit pause, do it by yourself, and then hit play. If you did number 1 by yourself, I still suggest you number 2 by yourself because there's something a little different this time. Okay, once again, I'm going to start by rewriting the equation so I have room to work. I have NaOH aqueous plus FeNO3 aqueous produces something. All right, so charges. Na is a 1 plus, hydroxide OH is a 1 minus. Fe is a not group 1A, 2A, or 3A cation, so we have to go backwards again. We know that NO3 is 1 minus. There are 3 of them, so that means you have a total negative charge of 3, which means we need a total positive charge of 3. Okay, and now the positives are going to switch places, so we're going to end up with FeOH, with Fe having a 3 plus charge, and OH having a 1 minus charge. Looks like we need to neutralize charges here, so we're going to end up with FeOH3. Plus, we have Na with a 1 plus charge, and NO3 with a 1 minus charge. Okay, so now we need to figure out which are aqueous, which are products, meaning solid, liquid, or gas. So we'll check the solubility rules. Okay, so we have FeOH3. OH is a hydroxide. And hydroxide, most are insoluble, except when bonded with NH4, group 1A metals, and Ba, Ca, and Sr, which is not true of FeOH3, which means he is going to be a solid because he's insoluble. Okay, then we have NaNO3. NO3 is a nitrate. All nitrates are soluble, so that means he is going to be aqueous. Okay, so we have FeOH3, which is a solid, and NaNO3, which is aqueous. Okay, so we finished our double displacement portion of creating net ionic equations. So next up is the complete ionic equation, where we're going to separate everything into ions. So we're going to have Na1 plus OH1 minus plus Fe3 plus NO3 1 minus, and that produces FeOH3 plus Na1 plus NO3 1 minus. All right, there is our complete ionic equation. So now we need to cross out our spectator ions. Remember, ions that are found on both sides. So it looks like we have sodium ion on both the reactant and the product side, so he is definitely a spectator, not involved. Hydroxide is an ion on the reactant side, but he is part of the solid product, which I neglected to write solid. Let me put that in there. So he stays. Iron is an ion on the reactant side, but part of the solid product on the product side. And nitrate is also a spectator ion because he is found on both sides of the equation as an ion. Okay, so now let's rewrite this as a net ionic equation. So we have OH1 minus plus Fe3 plus producing FeOH3. Okay. So now, this particular problem we're going to have to balance, and there are two different ways you can look at balancing it, coming up with the same answer. You can look at the number of atoms versus ions of each type. So, for example, we have one Fe there and one there, so those are fine, they're balanced. And we have one OH here and 3 here, not fine. So the way we'd fix that is by putting a 3 in front of the OH, then it's balanced. The other way you can do it is look at the charges on the reactant side. The charges need to be neutral, even though they're not hooked up. So I have 1 OH, 1 negative and 3 positives. So to fix that, we need to put a 3 here. Okay, either way, you get the same answer. So that is the final answer for the net ionic equation. All right, that's it for today.